Huh. Hello.
We're going to start section 9.5. This is our last section in chapter 9. It's called solving trig equations. We won't finish this today. We'll finish it on Friday. So between today and Friday, we'll work through section 9.5. We'll try to do as many WebAssign examples as we can. And then notice on Sunday is the homework for section 9.5. Okay. Also, folks, remember these WebAssign homeworks are all opened up in chapter 9 and 10 until April 7th. No, I'm sorry, until May 1st, which is the end of the semester. Okay, so all the WebAssign homeworks in chapter 9 and 10 are open until May 1st, but don't postpone the homeworks if you can. Try to stay on schedule. All right, then you can see on Monday, we'll do a review of chapter 9, and then next week we start in chapter 10. All right, folks, just a quick reminder that I'm recording the meeting today, so by joining the class today, you consent to being recorded. And does anyone have any questions so far in chapter 9? Anyone have any WebAssign questions? All right, well, folks, here's what we're going to try to do. We want to be able to now take trig equations and solve them. So what does that really mean when we want to solve a trig equation? Well, what it really means is you're going to want to find angles. So you want to find angles, I'll say theta, right? We use theta to mean an angle. So we want to find angles that satisfy a certain equation. What that really means is if I take my answer, theta, and plug it back into some starting equation, I end up with a true equation. Okay, so our answers in this section are going to be angles. And remember, we could write an angle in degrees, or we could write an angle in radians. That's up to you. Generally, WebAssign takes answers either in degrees or radians. The only thing you have to be careful about is if you enter an answer in degrees in WebAssign, you got to be sure to put this degree symbol. Otherwise, WebAssign assumes you're entering an angle in radians. All right, so let's take a look at some examples. Now, in general, we're going to be looking at two types of equations in section 9.5. We might be working with a linear equation down here in the lower left-hand corner, or we might be working with a quadratic equation. So this is really the first step. Ask yourself, is the equation linear or quadratic? Because you're going to have to solve these equations in two different ways. So how will you know if the equation's linear or quadratic? Well, what you do is you look at the trig function. If you see the trig function is just sine x or cosine x, that's a linear function. Because really these trig functions are being raised to the exponent 1. But a problem might have a sine squared x or a cosine squared x. And of course, if the exponent is 2 on the trig function, that's how you know it's quadratic. All right, so look at the trig function. If it has an exponent 2, it's quadratic. If it doesn't have an exponent 2, it implies the exponent is 1, so it'll be linear. All right, so that's step 1. here's a step-by-step process that we can follow to solve these equations. All right, well, I mentioned this first step. Figure out if the equation's linear or quadratic so you can determine the solution method you're going to use. Also, check out if there's only one trig function in the equation. So maybe the equation just has sine or cosine in it. We'll do some examples, and then we're just going to solve the equation for that function. But there might be more than one trig function in an equation. For example, maybe there's a sine and a tangent function. So for that, you're going to want to get the equation equal to 0 and then try to factor and do some solving. All right. Also, if the equation is quadratic, we could use the factoring method. So I'll remind you of what we talked about on Monday. So on Monday, we mentioned that if you're solving a quadratic equation, you can use three methods. You can use a square root method, or you can use a factoring method, or you can use the quadratic formula. So when we get a quadratic trig equation, we're going to check out these options. And remember, these options are in order from easiest to most complicated. So if we can use the square root property, we'll use that. If we can't use the square root property, we'll try to use factoring. If we can't factor, we'll have to use the quadratic formula. Okay? All right, so as we work through this, by the way, if anyone wasn't here for Monday's discussion about solving quadratic equations, let me just go back to Canvas for a second. So in Canvas, in our course, just a reminder, click on Zoom. And then you have to click up here on this tab that says Cloud Recordings. And this gets you to the recordings. Also, if you go to modules, you can access these closed captioning recordings. All right, so let's do some examples to jump into this. Of course, you're going to have the unit circle by your side. So keep this unit circle handy. We're going to need this to help solve the WebAssign questions we're going to work on. All right, folks, what we're going to try to do is today's class will focus mostly on linear equations, and Friday will focus mostly on quadratic. Okay? All right, let me go to a quick example here. Here's an example that says solve this equation. So I'm noticing this equation says 2 sine theta plus 1 equals 0. I want to solve this equation. Now, most of the problems you work on are going to also give you an interval. Remember, what that means is any answer you come up with has to be an answer inside of this range. Remember, you're going to try to find theta in these examples. So what this problem is telling you is theta can only be an answer in between 0 and 360 degrees. You might notice this interval has a bracket on the 0, but then a parenthesis on the 360. Well, if you remember interval notation, what that means is 0 itself is okay, but 360 itself is not okay. So really, your answer has to be any angle in between 0 and 359 degrees. I can't come up with an answer of 360 degrees exactly, because this parenthesis here tells me the number 360 is not allowed as part of the interval. All right, well, first question. Is this equation linear or quadratic? Well, when I look at the sine trig function, it's really sine to the exponent 1. So I know this is linear. So if it's a linear trig equation, what I'm going to do is just try to get sine theta by itself. I mean, you remember solving a linear equation like 2x plus 5 equals 19, for example, right? If you were solving this simple linear equation, your goal would be to get x by itself. Well, that's exactly what we're going to do here. We're going to try to get the trig function by itself on one side. So let me do that. To get started, I'm going to subtract 1 from both sides of this equation. When I do that, I get 2 sine theta equal -1. Then I'm just going to divide both sides of the equation by 2 in order to get the sine function by itself. So I end up with sine theta equals -1/2. All right, so I need an angle whose sine is equal to -1/2. Well, this is where the unit circle is your best friend, because I'm going to go back to the unit circle and I need the sine to equal -1/2. Well, remember, when you look at the unit circle, the cosine is the x value and the sine is the y value. So our example was sine theta equal -1/2. So all I have to do to answer this question is go around the unit circle looking for where the y value is equal to 1/2, because the y is the sine of the angle. So let me do a little bit of a search here. I'm noticing here is a sine, a y value equal to -1/2. So I can see one answer is 210 degrees. But I can't stop there because there could be more than one answer. And I'm noticing over here is another entry where the y value is -1/2. And that angle looks like 330. And that's it. There's no other angles on the unit circle that have the sine equal to -1/2. So I'm ending up with these two answers, 210 degrees or 330. I could write the answers in radians if I want. 210 is the same as 7 pi over 6. 330 is the same as 11 pi over 6. WebAssign should take either one of these answers. Totally up to you. So if I go back to this problem, whoops, here it is. To go back to this problem, you can see the two answers here are 210 and 330 degrees. Now, why did this problem say to use the interval 0, 360 anyway? What's the point? Why do we need that since there were only two answers on the unit circle where sine theta was equal to -1/2? Well, the reason they give that interval is because, technically speaking, there could be infinite number of answers to these kinds of questions. Because even though 210 is a valid answer, what if you were to rotate all the way around the unit circle and come back to 210? Well, that would mean that 210 plus 360 is another valid answer, right? So really, technically, another valid answer to this question is 570 degrees. The same thing for 330. I could rotate all the way around the unit circle, a full rotation, and then go back to that 330 degree position. So technically, another valid answer to this question is 690 degrees. And I don't have to stop there. Instead of rotating once around the unit circle, I could rotate 2 times around the unit circle and then go back to 210. So to avoid, many answers, they give us this interval to really say restrict your answers to just one revolution around the unit circle, one rotation. Okay? If they didn't say that, technically there would be an infinite number of solutions to these kinds of questions. All right, let's do some WebAssign examples just so you can see the setup of these. All right, let me go to this top example to start with. We'll use the unit circle here to help us out. All right, well, I'm going up to the top example, and it says 2 sine theta equals -2. First, I'm noticing this is a linear equation. All right, well, that means I just want to get sine theta by itself on one side. Well, to do that, I'm just going to divide both sides of this equation by 2, because that'll get sine theta by itself. If I do that, the 2's on the left side cancel out, and I end up with sine theta equals -√2 over 2. All right, now I just have to figure out theta. Really, it's asking what angles have the sine equal to -√2 over 2. Well, I know that when I go to the unit circle, the sine is the y value. So I'm going to go on a little bit of a scavenger hunt here. I'm looking for where the y value is -√2 over 2. So here it is, one location. It looks like the angle is 225 degrees or 5 pi over 4. So that's one solution. But remember, there could be more than one solution to these equations. So I'm going to keep looking, and I'm noticing down here in the lower right corner is another y value that's -√2 over 2. That answer, that angle, looks like it's 315 or 7 pi over 4. So 2 answers to this question. Can I do a full rotation around the unit circle to get another answer? No, I can't do it because they said your answers have to be on this interval between 0 and 2 pi. That really means restrict your answers to just one rotation around the unit circle. All right, does that make sense? So some of these linear equations I think you're going to find are not that complicated and not that time consuming, because all you have to do is get the trig function by itself, then go to the unit circle and find the angles that satisfy the equation. All right, let me go to the bottom example. So the bottom example says 8 cosine theta equal 4. I'm noticing this is linear because it's really cosine to the exponent 1. So that means I'm going to try to get cosine by itself on the left side. To do that, I'll divide both sides by 8. So I'm ending up with cosine theta equals 4 over 8. But of course, 4 over 8 is the same as 1/2. So now I'm going to go to the unit circle looking for where the cosine, what angles have the cosine equal to 1/2. Well, I remember the cosine is the x value on the unit circle. So let me go looking around the unit circle. Where is the cosine equal to 1/2? Well, this angle 60 degrees has the x value equal to 1/2. So one answer is going to be 60 degrees, or I can write it as pi over 3. And there's another answer, because if I come down here to the very bottom, you might notice that 300 degrees also has the x value equal to 1/2. So a second answer is 300 degrees or 5 pi over 3.
Was it 300 or 30 or one?
Well, I'm looking down here, Jannar. Remember, our equation is cosine theta equal 1/2.
Okay, that's 300 then.
Yep, 300. If it was sine theta equal 1/2, then yes, the answer would be 30 degrees, but because it's cosine theta, the answer is 300 degrees or 5 pi over 3. Now you might say, well, all of these questions have two answers. Do you think all of these questions will always have two answers like these examples we just did?
Those are the three answers.
Yeah, well, notice for the top problem we worked on, we came up with actually two answers here. And for the bottom problem, we also happened to come up with two answers. So there were two angles for each of these examples. Is that always going to be the case? The answer is no. It's going to depend on the particular problem you're working on. Some problems might just have one answer. Some problems might have two answers, like these examples. Some problems could have 4 answers. Some problems could even have 8 answers. So it all depends on the problem. Don't assume that every problem is only going to have 2 answers just because of these examples we did here. All right, let me go do a couple more examples. All right, here's one that's a little trickier because it involves the tangent function. So it says tangent of theta equals -1. So I need to find angles where the tangent is equal to -1. Why is this a more complicated problem than the examples we did a minute ago? What makes this a more complicated problem, would you say? Well, in the other examples we did, it involves sine and cosine. And sine and cosine are readily available on the unit circle. The problem is the tangent is not on the unit circle. So here's a suggestion, folks. Why don't you work out the tangent for each one of these angles yourself? How do you do that? Well, go back to the definition of tangent. And remember, the definition of tangent for any angle is taking the sine over the cosine. So how about if I work this out for a couple of angles? So let's do it. How about if we want to find the tangent of 30 degrees? All right, well, the tangent of 30 is sine 30 over cosine 30. So let me go grab the sine of 30 and the cosine of 30 from the unit circle. Well, sine of 30 is 1/2. Cosine of 30 is square root of 3 over 2. Right, folks, remember the y value is the sine.
And x value is a cosine.
X value is a cosine, yep. All right, well, do you remember how to divide fractions? You keep the top fraction as is, change to a multiplication, and then take the bottom fraction and flip it upside down. So I'm going to flip this bottom fraction upside down, and that's going to be 2 over square root of 3. All right, well, I'm noticing the 2 on top cancels out with the 2 on the bottom. So the tangent of 30 degrees is 1 over the square root of 3. So in purple, I'm going to write the tangent for these angles over here. So the tangent of 30 is 1 over square root of 3. Now, a good idea would be for you to do this on your version of the unit circle. So you only have to calculate these tangents once. You don't have to go back and redo this every time. So if you write this down on your copy of the unit circle, you'll have it available. All right, let me do 1 or 2 more of these angles. Let's do tan of 45 degrees. Well, tan of 45 means I'm going to take the sine of 45 divided by cosine 45. Well, the sine of 45 is square root of 2 over 2. The cosine is also square root of 2 over 2. So let me divide these two fractions. So it's going to be the square root of 2 over 2 times, I got to flip the bottom fraction upside down. So that's going to be 2 over the square root of 2.
And the 2's cancel out the 2's.
Yeah, the 2's cancel out, and also the square root of 2's cancel out top and bottom. So this answer is just 1. You probably could have seen that because this tangent of 45 degrees turned out to be 1 fraction divided by itself, right? Because sine 45 and cosine 45 are the same value, anytime you take one quantity divided by itself, you always get 1. All right, so in purple, I'm going to write the tangent of 45 is equal to 1.
That's right.
Let me do the same analysis, just one more angle. Let me do tan 60 degrees. All right, well, tan 60 is going to be sine 60 over cosine 60. Sine 60 is square root of 3 over 2. So this is going to be square root of 3 over 2. Cosine 60 is 1/2. So now I'm going to keep the top fraction, change to a multiplication, and flip the bottom fraction upside down. And I'm noticing now there's a 2 on top that cancels out with the 2 on the bottom. So this is going to be the square root of 3 over 1, which is just the square root of 3. Now I know the tan of 60 degrees is the square root of 3. I'll write it here on the unit circle. So these are the tangents that I can keep handy. Now, since I went to this trouble, it's actually easy now to fill in tangent for all the other angles. Let me go to tangent 120. I really don't have to do any work because when I do the tangent of 120, it's going to be the same calculation as tan 60. The only difference is it's going to be a positive divided by a negative. So just looking at the sine and cosine of 120, I can see right away the answer here is going to be negative square root of 3. Let me go to tangent 135. Well, I could see for tangent 135, it's a quantity divided by itself, but it's going to be a positive divided by a negative. So I could see the tan of 135 is going to be negative 1. And finally, the tan of 150. Well, that's going to match up to the tan of 30. It's the same calculation. But again, it's just going to be that it's going to be a positive divided by a negative, which is a negative. So the tan of 150 is going to be negative 1 over square root of 3. All right, so the only reason I went to this trouble is to help you figure out the tangent of every angle on the unit circle. If you want, good idea is to write this down on your copy of the unit circle. So you can kind of do it once and not have to repeat the tangent calculations. All right, well, with all that, let's go back to this problem. It wants
Yeah.
me to figure out where is the tan equal to -1.
Wait, how'd you find answers of 3 pi over 4 and 7 pi over 4?
Which angle are you referring to, Gennaro?
It says data equals the answers that we didn't got was says 3 pi over 4, then 7 pi over 4 as the answers. It says.
Yeah, let's get to that. Okay, so I need to figure out tan of an angle equal to -1. Well, I know because the tangent is sine over cosine. If this answer is going to be -1, the only way that can happen is if the sine and the cosine are the same value, but different signs. So what angles have the sine and cosine equal to each other, but different signs? And you can see we kind of started out calculating the tangent of 45 was equal to 1. Right? So I know tan 45 is equal to 1. Because when you look at 45 degrees, the sine and the cosine are the exact same value. So when I divide sine by cosine and get tangent, it's just 1. But how about the tangent of 135? Well, the tangent of 135, we already calculated to be -1. And that makes sense because notice the sine and the cosine are the same value here, but just different signs. So one answer to this question is theta equal 135, which is the same as 3 pi over 4. And again, the way I knew that, the way I figured that out is I said to myself, if the tangent is going to equal -1, the only way that can happen is if the sine and the cosine are the same value, but opposites of each other. Is there another angle on the unit circle where the sine and the cosine are equal, but just different signs? One is positive, one is negative. How about the tangent of 225? Can anyone comment on what is the tangent of 225? Is it +1 or -1?
Tangent of 225.
Remember, the tangent is taking the sine divided by the cosine. So here's the sine, -√2/2. Here's the cosine, exactly the same, -√2/2. What happens when you take a quantity and divide it by itself? Well, you get 1. And this is a negative divided by a negative, so the tan of 225 equals +1. So that's not an answer to this question, right? Because I need the tangent to equal -1. But let me come over here to 315 degrees. What is the tangent of 315? Well, it's sine over cosine. But in this example, the sine and the cosine are the same. It's just that the sine is negative and the cosine is positive. So does it make sense? This answer for the tangent here is going to be -1. So the second answer here for this problem is 315 degrees or 7 pi over 4. All right. Folks, this is a little messy here, I think. Let me recap. Let me clear everything and I'm going to recap here. All right. Here's the question they asked me. What is tan? Solve tan theta equal -1. So I need the angles where the tangent equals -1. The problem is the unit circle isn't showing me tangent. But as I just demonstrated, you can figure out the tangent yourself for each one of these angles by just taking the sine of that angle divided by the cosine of that angle. I can also take a little bit of a shortcut because for 45 degrees, when I take sine divided by cosine, it's a quantity times itself. So what we said is right away, without doing any work, you can see that tan 45 has to equal 1. It was the same thing down here for tan 225. Because I'm taking a quantity divided by itself, so tan of 225 was also equal to positive 1. And then we looked at these angles. What about 135? Well, the tan of 135 turns out to be negative 1. How do I know that? Well, I'm just going to take sine over cosine. And if you take the sine divided by the cosine for 135, you get the answer, negative 1. And it's the same deal if you were to calculate the tan of 315 by taking sine divided by cosine. If you work it out, you would see that tangent is also negative 1. So remember, this problem said, where is the tangent equal to negative 1? So the two answers were 135 degrees and 315 degrees. You could enter your answer in degrees or in radians. That's totally up to you. All right. Everyone okay? Please don't be shy about asking questions, folks, if this doesn't make sense. But the tangent is just a little trickier to work with because tangent is not on the unit circle. All right, let's just do a couple more examples here just to help you work through WebAssign. And again, I'm noticing these two examples on this slide are both linear examples. So if they're linear examples, all I'm going to do is try to get the trig function all by itself. So let me come over to this one. I want to get cosine by itself on one side of the equation. To do that, I'll divide both sides by 4. When I do that, I'm getting cosine theta equals negative 2 over 4. But that's negative 1/2. So for this answer, I'm going to go around the unit circle, looking where the cosine is equal to negative 1/2. I know the cosine is the x value, so here is one answer. So it looks like one answer is 120 degrees. And I'm noticing here is another answer where the cosine is negative 1/2. So another answer would be 240 degrees. All right, let's go to the bottom example here. It says 2 sine theta equals negative square root of 3. So I want to get the sine all by itself. For that, I'm going to divide both sides by 2. That's going to leave me sine theta is negative square root of 3 over 2. Of course, the sine is the y value on the unit circle. So let me go try to find the y values with negative square root of 3 over 2. Let's look around
150,
here.
150. I'm sorry, that's for cosine.
Yeah, so it looks like 240, again, has its sine equal to negative square root of 3 over 2. So looks like one answer is 240.
Then 300.
Good. 300 is the other answer because here is the sine equal to negative square root of 3 over 2. So the other answer is 300. Again, you can enter your answer as either degrees or radians, totally up to you. Now, you might say, well, when is there an example of one answer only? What could be an equation? Because in all these examples we've done so far, we ended up with two answers or two solutions. So what might be an example where you end up with just one answer? Let me give you a quick example or two. So let me give you a quick example. How about if I said 10 sine theta equals 10? Well, for this example, I'd want to get sine theta all by itself, so I'm going to divide both sides by 10. So that means sine theta equals 1. All right, what's the answer to this equation? What angle has its sine equal to 1?
Sine equals to 1, and we'll make it, there's a 90 degrees.
Good, 90 degrees, or pi over 2. Is there any other answer? Is there a second answer for this one?
I mean, first of all, I can't see the bottom one.
Oh, sorry about that. Yeah, this bottom one, let me see if I can do that. Hang on one second, Gennaro. Let me see if I can move this up a little bit. Aha.
That's -1, so only just one of them.
Right, one answer to this equation. So in this particular example, there's only one answer.
Just 90 degrees.
Yeah, let me give you one more example here. How about -7 cosine theta equals 7?
You have to divide this -7.
Divide both sides by -7. Yep, good. And if I do that,
-1.
Cosine theta equals -1. So let me go to the unit circle and look what angle has its cosine equal to -1.
180.
So in this example, the answer here is theta equals 180.
Then in pi.
Or pi. Is there any other solution?
Only just see one of them.
Yep. So again, this example just has one solution. So don't always assume that you have two answers. It could be, depending on the problem, that there might just be one solution. On Friday, when we do some examples, this is going to turn out to be 4 solutions or 8 solutions or even more. So it all depends on the problem you're working on as to how many solutions there might be. All right, folks, we're almost out of time. Let me just mention one more item. So, of course, everything we've done today has been linear equations. But we might want to solve quadratic trig functions, trig equations. So we're going to come back to this property that we talked about on Monday, that says when you're trying to solve a quadratic equation, if you can get this to look like x plus a quantity and x minus, let's just say x plus another quantity set equal to 0, we call this factoring, then you're allowed to set one parenthesis equal to 0 and the other parenthesis separately equal to 0. So then you break this up into 2 equations where you set each parenthesis separately equal to 0. That's what this statement is trying to tell you up here. It says if you have one quantity multiplying another quantity and it's equal to 0, you're allowed to set the first quantity equal to 0 or the second quantity equal to 0. So we're going to need this factoring method to solve quadratic trig equations. Let me do one quick example to wrap up. Let me go to the next slide. We'll do more examples next time, but I just want to do one quick example here. All right, here's the equation they're giving us in this example. It says sine theta tan theta equals sine theta. All right, this is a little bit of a tricky equation to solve. Let me jump back to the instructions, because if I can jump back to the instructions, maybe we can figure out how to get started. All right, here are the steps. Look at the very bottom of the slide. It says if more than one trig function is present, get the equation set equal to 0, then try to factor the one side of the equation. Well, in our example, we did have more than one trig function, right? We had a sine and a tangent. So let's go back there, because now the instructions said get the equation set equal to 0 as the first step. So what I'm going to do for that is I'm going to subtract sine theta from both sides in order to get the equation set equal to 0. On the right side, sine theta subtract sine theta gets me a 0. And on the left side, I have sine theta tan theta subtract sine theta. But now what I want to do is factor, do some factoring. So when I look at the left side of this equation, do you notice sine theta is showing up in the first part and in the second part here? Well, that means I can factor out a sine theta in front of the parenthesis. So I'm taking out a sine theta in front. If I do that, what I'm left with is tan theta minus 1. But this is where I have, one quantity multiplying a second quantity equal to 0. So I'm going to break this up into two equations now. The first equation is sine theta equals 0. And the second equation is tan theta minus 1 equals 0. And now I'm going to solve each one of these equations separately. Let me go and solve sine theta equals 0. Well, I know that means the y value has to equal 0. So for that, let me jump back to the unit circle. So I have sine theta equals 0. Okay, let me jump back to the unit circle. I need the y value to be equal to 0. So I'm noticing on this slide, there's a couple of answers. Here is the y value equal to 0. So it looks like 0 degrees is one answer. Here's another angle where the y value is equal to 0. So another answer is 180. One other thing I'm noticing, though, is here's another angle that has the y value equal to 0, 360. Can I use 360, though, as part of my answer? No, I can't use 360. The reason is it's not part of the allowed interval. So if I go back to that example, notice they said here you're only allowed to use the interval 0 to 360, but not including 360 itself. Remember, that's what this parentheses means. So for this equation, I'm ending up with two answers, 0 and 180. The other equation that I wanted to solve was tan theta minus 1 equals 0. Well, let me add 1 to both sides. And when I add 1 to both sides, I get tan theta equal 1. So what angles have the tangent equal to 1? Well, this is why it's nice to have the unit circle marked up where you wrote down the tangent for each angle, on your copy. And a few slides ago, we worked this out. Tan theta was equal to 1 for 45 degrees and 225 degrees. So notice for this problem, there's 4 answers. right? I have two answers for the one equation. The one equation was sine theta equals 0. That got me two answers. The other equation was tan theta equal 1. That got me two other answers. So in this problem, there's four answers. All right, folks, I just want to show you that on Friday, we'll look at some more complicated examples. You might notice this example has two trig functions. This example has secant and sine floating around. So we're going to have to solve this equation in the same kind of way. Another example here, sine and tangent mixed in. So we'll have to solve this equation in the same kind of way. This example we'll look at is going to be a factoring example, okay? And then I'll just mention this is the last slide. Notice here, this is a cosecant squared. Well, whenever I see a trig function with an exponent 2, I know this is going to be a quadratic equation. So we're going to have to solve these kinds of trig functions in a different way using the methods to solve quadratic equations. All right, folks, I think we're out of time. So let me wrap up here. Again, the focus today was solving trig equations that are linear in nature. On Friday, we'll focus on trig equations that are quadratic. Anyone have any questions on any of these WebAssign examples? All right, if you do have questions, please feel free to stick around for a few minutes. If you don't have questions, feel free to log off.
Can we solve the cosecant squared x minus 4 equals 0 real quick?
We were going to do that next time, Gennaro, but if you want to stick around, I can do this now. Yeah.
Okay, we can do it right now if you like.
Yeah. Let me just see if any students have any other questions. Anyone have any other questions on solving linear equations? All right. So, folks, let me work through this example. Now, we're going to do this again on Friday, so don't worry if this is a little confusing to you, because we'll do this on Friday. Let's get started. So what I'm seeing on this one is that it's cosecant squared. Now, let me go back to the previous slide for a second.
We have the square root.
Yeah, so here is the way to handle an equation that looks like something squared equals a number. You take the square root of both sides, right? This is called the square root property, and we talked about this last class. So that's really the format for this example that we're looking at. It is a quantity squared. To get started, let me add 4 to both sides of this equation. Okay, so I'm going to add 4 to both sides. When I do that, I'm getting cosecant squared equals 4. All right, but usually I don't like to work with cosecants because cosecant is not on the unit circle. Only sine and cosine are on the unit circle. So let me get rid of cosecant, and I'm going to replace it with 1 over sine. So this is going to end up being 1 over sine squared equals 4. Right? Does that make sense? Because if cosine squared, if cosine is 1 over sine, if I were to square both sides of this equation, that would tell me cosecant squared is 1 over sine squared. All right, let me try to solve this equation now. But I'd like to get rid of fractions. Here's a little trick I can use to get rid of fractions. Let me put the 4 as 4 over 1. So I'm going to write 4 as a fraction, 4 over 1. Whenever you have one fraction equal to another, you can cross multiply. So I'm going to cross multiply. If I cross multiply, that means 4 sine squared x equals 1. All right, so at least I got rid of fractions. Let me get the sine squared all by itself. So I'm going to divide both sides by 4.
Then you get 1 over 4 for.
Yep, so I'm left with sine squared equals 1 over 4. But of course, I don't want sine squared, I want just sine. Well, the square root property that we looked at on the last slide says take the square root of both sides. So I'm going to take the square root of both sides. But here's where I got to be careful. You have to remember when you take the square root of both sides, you have to put a plus or minus symbol in front of the right side here. So now let me take the square root of both sides. What it's leaving me with is sine x on the left side is plus or minus the square root of 1 over 4. What is the square root of 1 over 4? Square root of 1 over 4 is 1/2. All right, but now I got to think of this as really two separate equations. The one equation is sine x equal positive 1/2 and sine x equal negative 1/2. So the tricky part of this problem is recognizing that when you took the square root of both sides, you had to include this plus or minus symbol. If you forgot the plus or minus, you're not going to get this problem correct. All right, now I'm just going to go to the unit circle. What angles have the sine equal to 1/2? Well, 30 degrees is one answer. Remember, the sine is the y value. 150 degrees is another answer. All right, so those are the angles that have the sine equal to positive 1/2. What angles have sine equal to negative 1/2? Well, if I come down here, 210 is one angle that has sine equal to negative 1/2. And let me look, here's another angle that has the sine equal to negative 1/2, so 330. Again, notice there were 4 answers to this problem. I shouldn't say theta here, I should say x. Okay, so this turned out to be a quadratic equation because we were dealing with a cosecant squared. We changed that to be sine squared. And for this example, we were able to use the square root property to solve the quadratic equation. All right, folks, any questions on this one? Again, we'll redo this on Friday because I know some students dropped off. But for anyone that was interested, this is how to work through this WebAssign example. All right, folks. Well, thank you for joining. We'll meet again on Friday. Please try to get started in the 9.5 homework. And if you have any questions, we can talk about it on Friday's class.
I already finished 9.5.
All right. Nice work, Gennaro. All right, folks. Thanks again, and we'll talk on Friday.
Okay. Bye.
Bye, everyone.